January 1943. Somewhere along the cold, restless waters of the North Atlantic, a convoy cuts through the darkness, slow, heavy merchant ships carrying fuel, steel, and men. The sea is black, the sky empty, no searchlights, no warning. Beneath the surface, unseen and silent, a German U-boat waits. Inside one of the escort ships, there is no shouting, no panic, only the low hum of equipment and a steady pulse echoing through a headset. A signal, faint but unmistakable. Not a man, not a weapon. A machine has found the enemy. Miles away, in a dimly lit room filled with wires, rotating drums, and scattered notes, another kind of battle unfolds. No explosions, no uniforms, only patterns and a race to break them before lives are lost at sea. And high above the clouds, beyond the sight of both hunter and hunted, invisible waves travel outward, guiding, detecting, calculating. The war is raging across continents, but its outcome is being shaped in places no one will ever see. Not on the front lines, but in silence. And it is here, in these forgotten moments, that victory quietly begins to take form. One signal, one circuit, one unseen breakthrough at a time, leading us into a world where technology would change the very nature of war itself. September 1939. War returns to Europe with a speed and violence that few had truly anticipated. When Germany's invasion of Poland begins, it is not a slow grind of trenches like the First World War. It is fast, coordinated, mechanized. Columns of German armor push forward with precision. Aircraft strike ahead of advancing troops. Communication flows rapidly between units. The world witnesses a new form of warfare, blitzkrieg, lightning war. Within weeks, Poland collapses. By the spring of 1940, the pattern repeats itself. Denmark falls in hours. Norway struggles under sudden assault. Then, in May, German forces surge into Western Europe. The fall of France shocks the world. A military power long considered dominant is defeated in just 6 weeks. Across the English Channel, Britain stands alone. But even as the war spreads across land, another battlefield emerges. Vast, cold, and unforgiving. The Atlantic Ocean becomes a critical artery of survival. Supplies from North America must reach Britain, or the island nation will slowly starve under blockade. Germany understands this. Its answer lies beneath the waves. U-boats, submarines, begin hunting in coordinated groups known as wolf packs. They strike at night, surfacing silently among convoys, launching torpedoes before slipping back into darkness. Merchant ships burn. Sailors vanish into freezing water. Entire supply lines begin to fracture. At this stage of the war, the advantage is not with the defenders. Detection is primitive. Escorts are few. Communication is limited. A submarine, once submerged, becomes almost invisible. The ocean itself becomes an ally of the attacker. By 1941, the situation grows increasingly desperate. Britain survives, but barely. Losses in the Atlantic mount. Every convoy becomes a gamble. Meanwhile, across the world, another power expands rapidly. Japan advances across East Asia and the Pacific, seizing territory with speed and coordination. Its naval aviation proves devastatingly effective. Then, on December 7th, 1941, the war reaches across the ocean. The attack on Pearl Harbor brings the United States into the conflict. The entry of the United States changes the scale of the war overnight, but not its immediate balance. Because in early 1942, America is not yet ready. Its army is expanding but inexperienced. Its navy is recovering from heavy losses in the Pacific. Its industrial strength is immense but still mobilizing. And its enemies, already hardened by years of war, hold the initiative. German U-boats now extend their operations to the American coastline. Tankers burn within sight of shore. Oil slicks spread across the Atlantic. The war, once distant, is now immediate. On land, Axis forces press deep into Soviet territory. In North Africa, battles shift back and forth across the desert. In the Pacific, island after island falls under Japanese control. Everywhere, the pattern is the same. The Axis powers move fast, strike first, and exploit weaknesses before their enemies can respond. For the United States and its allies, the challenge is not just to fight, but to adapt. Because matching the enemy tank for tank, ship for ship, or plane for plane may not be enough. The speed and coordination of Axis operations reveal something deeper. War is no longer decided by numbers alone. It is decided by information, by detection, by coordination. And in these early years, those advantages often belong to the other side. But beneath the surface of this struggle, something begins to shift. Not on a battlefield. Not yet. In laboratories. In factories. In quiet rooms filled with engineers, mathematicians, and machines. A different kind of war is beginning to take shape. One that will not rely solely on firepower, but on innovation. And as the pressures of global conflict intensify, the United States begins to realize that its greatest strength may not lie in what can be seen, but in what can be built. A realization that will lead directly into an unprecedented mobilization of science, industry, and imagination, setting the stage for technologies that will quietly, but decisively, change the course of the war. Early 1942. The United States is now fully at war, but unlike the Axis powers, it is not yet defined by battlefield victories. Its strength lies elsewhere. Vast, untapped, waiting to be organized. Factories that once produced automobiles begin to fall silent, only to restart with a different purpose. Assembly lines are reconfigured. Steel is redirected. Civilian industry transforms into an engine of war. But this transformation is not only industrial. It is intellectual. Across the country, universities, laboratories, and private companies are drawn into a coordinated effort unlike anything seen before. Scientists who once studied abstract theories are now tasked with solving immediate, life-or-death problems. How do you detect an enemy you cannot see? How do you guide aircraft across oceans in darkness? How do you strike with precision from miles above the earth? These are not questions for generals alone. They are questions for physicists, engineers, and mathematicians. And so, a new kind of alliance begins to form, one between government, science, and industry. Organizations emerge to coordinate this effort. The Office of Scientific Research and Development becomes a central force, connecting military needs with civilian expertise. Under its direction, thousands of projects begin, many of them classified, hidden even from those fighting on the front lines. At institutions like the Massachusetts Institute of Technology Radiation Laboratory, research accelerates at a pace driven by urgency. Radar, once experimental, begins to evolve rapidly. New systems are designed to detect aircraft at greater distances, track ships in darkness, and even identify submarines on the ocean surface. These are not incremental improvements. They are breakthroughs. Meanwhile, deep within secure facilities, another silent battle unfolds, one of codes and ciphers. Enemy communications, once thought secure, become targets. Machines are built not to destroy, but to decipher. Patterns are analyzed, signals intercepted, meaning extracted from chaos. The goal is simple: know the enemy's intentions before they act. In parallel, the challenge of navigation becomes critical. The war now spans continents and oceans. Aircraft must travel vast distances, often at night, often through clouds, often under threat. Traditional methods are no longer enough. New electronic navigation systems begin to emerge. Signals transmitted across the airwaves guide pilots with unseen precision. Bombing accuracy improves. Missions once considered impossible become achievable. And then there are the factories. American industry does not simply produce, it innovates while producing. Standardization, modular design, and new manufacturing techniques allow complex equipment to be built faster and more reliably than ever before. The result is not just quantity, it is consistency. Weapons behave predictably. Systems integrate smoothly. Repairs become faster. Logistics, often overlooked, becomes a decisive advantage. But perhaps the most significant shift is philosophical. The United States begins to approach war not just as a contest of strength, but as a problem to be solved. Each challenge, submarines, air defense, communication, targeting, is broken down, analyzed, and addressed with focused precision. Failures are studied. Solutions are tested. Iteration replaces improvisation. And slowly, almost imperceptibly, the balance begins to change. Convoys become harder to attack. Aircraft find their targets more reliably. Enemy movements become less unpredictable. Yet, to those on the front lines, much of this remains invisible. A sailor may notice that fewer ships are lost, but not understand why. A pilot may reach a target through cloud cover, but not see the system guiding him. A commander may receive timely intelligence, but never know how it was obtained. These technologies do not announce themselves. They do not inspire headlines or dramatic recognition. They simply work, quietly, consistently, decisively. And as 1942 turns into 1943, the cumulative effect of these innovations begins to reveal itself, not as a single turning point, but as a series of subtle shifts that, together, reshape the battlefield. The Axis powers, once dominant through speed and coordination, begin to encounter resistance they cannot fully explain. Their advantages erode, not through direct confrontation alone, but through a growing network of unseen capabilities. Detection improves. Communication accelerates. Precision increases. War, once driven by visibility and force, is becoming something else, something quieter, more calculated. And it is within this transformation that the stage is set for the technologies that will define the conflict, not as symbols of power, but as instruments of quiet victory. Technologies that will soon reveal themselves through their impact as we begin to examine them from multiple perspectives. By 1943, the battlefield is no longer defined solely by what can be seen. It is shaped by what can be detected. Radar, once an experimental concept, has become one of the most quietly transformative technologies of the war. Systems developed and refined through institutions like the Massachusetts Institute of Technology Radiation Laboratory begin to spread across ships, aircraft, and coastal defenses. For the first time, distance and darkness lose their advantage. Aircraft can be tracked long before they are visible. Ships navigating through fog or night can identify threats beyond the horizon. Even submarines, when forced to surface, become vulnerable to detection from above. Complementing radar is another unseen system, sonar. Beneath the surface of the Atlantic, sound waves travel through water, reflecting off submerged objects. Escorts begin to hear what they cannot see. A submerged U-boat is no longer completely hidden. Then comes one of the most overlooked breakthroughs, the proximity fuse. Developed under the coordination of the Office of Scientific Research and Development, this small device changes anti-air warfare entirely. Instead of requiring a direct hit, shells can now detonate when they come close to a target. Accuracy increases dramatically. Aircraft losses rise. Airspace becomes more dangerous. None of these technologies rely on spectacle. They do not produce dramatic visuals, but they alter probabilities, quietly tipping the balance in favor of those who could detect, calculate, and respond faster than their enemy. While battles rage across continents, another war unfolds within American factories. It is a war of output, precision, and scale. The United States does not simply produce weapons. It redefines how they are made. Assembly lines, perfected in the automotive industry, are adapted for war production. Components are standardized. Processes are streamlined. The result is staggering. Aircraft roll off production lines at speeds previously unimaginable. Ships are constructed in weeks rather than months. Equipment is not only produced in massive quantities, but with consistent quality. But beyond volume lies a deeper advantage: integration. Radar systems fit seamlessly into aircraft. Communication devices are standardized across units. Spare parts are interchangeable. Repairs become faster, reducing downtime in critical operations. Logistics, often invisible in traditional narratives, emerges as a decisive factor. Supplies move efficiently across oceans and continents. Fuel, ammunition, and equipment arrive where needed when needed. This consistency allows commanders to plan with confidence. A strategy built on reliable systems becomes more than an idea. It becomes executable reality. And in this quiet efficiency, the United States begins to outpace its enemies, not just in numbers, but in cohesion. Behind every machine, every system, every quiet innovation, there are people. Not soldiers on the front lines, but individuals working far from the sound of gunfire. Engineers, physicists, mathematicians. Many of them had never imagined contributing to war. Their work, once theoretical or academic, is now directed toward survival. Problems that once existed in equations now carry immediate consequences. At facilities across the country, teams work around the clock. Failures are constant, but so is persistence. Each breakthrough is hard-earned, built on countless iterations and refinements. Unlike soldiers, their contributions are rarely visible. There are no medals for a successful equation, no headlines for a working circuit, and yet their impact is profound. A scientist improves radar sensitivity, and a convoy avoids ambush. An engineer refines a fuse, and an aircraft is brought down before it can strike. A mathematician deciphers a pattern, and a fleet changes course in time. These individuals do not witness the results of their work directly. They operate in fragments, small pieces of a much larger system. But together, those fragments form a network of capability that extends across every theater of war. A network that operates without recognition, without visibility, but with undeniable effect. And as these technological, industrial, and human elements converge, They begin to influence not just how the war is fought, but how it is understood. Because from this point forward, victory will not belong solely to those who fight the hardest, but to those who think, build, and adapt the fastest. A realization that becomes even clearer when viewed from the perspectives of strategy, enemy response, and the evolving morality of modern warfare. By mid-1943, battlefield decisions are no longer based solely on sight, instinct, or delayed reports. They're guided by systems. Convoy commanders in the Atlantic begin to rely on radar sweeps before making course adjustments. Escort ships position themselves not just by formation, but by signals received through sonar. What was once guesswork becomes calculation. In the air, navigation transforms entirely. Long-range bombing missions, especially over heavily defended regions like Germany, had once depended on clear skies and visual identification. Now, electronic navigation systems allow aircraft to find targets through cloud cover and darkness. Bombing becomes more consistent, not perfect, but far more reliable than before. Timing improves. Coordination sharpens. Fighter escorts can rendezvous more precisely. Bombers can maintain tighter formations. Entire spread across hundreds of miles begin to move with synchronized intent. Even artillery evolves. With the introduction of proximity fuses, anti-aircraft units no longer rely on precise timing calculations alone. Instead, shells detonate automatically near enemy aircraft, increasing effectiveness and reducing wasted fire. The result is subtle but decisive. Commanders begin to trust the data. Strategies become more complex. Operations become more ambitious. And as confidence in these systems grows, the scale of operations expands. Because uncertainty, once the greatest limitation, is slowly being reduced. For the Axis powers, the shift is difficult to understand because it is not immediately visible. German U-boat commanders begin to notice a change in the Atlantic. Convoys that were once easy targets now respond faster. Escorts seem to anticipate attacks. Aircraft appear overhead with increasing frequency, even in poor visibility. Losses rise, but the cause is unclear. From their perspective, the ocean has not changed. Their tactics remain sound. Their submarines are still capable. And yet, something is different. Detection feels faster. Reactions feel immediate. Opportunities disappear more quickly than before. In the air war, German pilots encounter increasingly accurate anti-aircraft fire. Explosions occur closer, more frequently. Survival margins shrink. There is no single weapon to identify, no obvious breakthrough to counter. Only a growing sense that the battlefield itself has become more hostile. Similarly, in the Pacific, Japanese forces face unexpected precision in American operations. Island assaults are better coordinated. Naval engagements unfold with greater awareness of enemy positions. From their viewpoint, the enemy seems to know more than it should. But without clear evidence, these changes are difficult to counter. Adjustments are made, but often too late or without full understanding of the underlying cause. Because the advantage lies not in a visible weapon, but in a system of technologies working together. A system that cannot be easily targeted because it is not concentrated in one place. War is often remembered through moments of visible heroism, charges, battles, victories marked by flags and territory. But these technologies introduce a different kind of power. one that operates without recognition. There is no dramatic moment when radar wins a battle. No single headline announcing the success of a navigation system. No ceremony for a breakthrough in signal processing. Instead, there is accumulation. Small advantages repeated over time. A convoy saved here. An aircraft intercepted there. A mission completed more accurately than before. Individually, these moments seem minor. Collectively, they're decisive. This raises a deeper question, one that extends beyond the war itself. What defines victory? Is it the visible act of combat, or the unseen systems that make that act possible? For the soldiers, sailors, and airmen on the front lines, courage remains essential. But increasingly, their survival and success depends on factors beyond their immediate control. Machines calculate, signals guide, systems inform decisions. Human bravery is still present, but it is now supported and sometimes overshadowed by technological precision. And in this shift, warfare begins to change, not just in how it is fought, but in how it is understood. Because from this point forward, the most decisive advantages may not be those that can be seen or celebrated, but those that operate quietly, shaping outcomes without ever revealing themselves. A reality that becomes unmistakable when these technologies converge at critical moments, moments where the course of the war itself begins to turn. Spring 1943. The Atlantic Ocean, once a vast hunting ground for German U-boats, begins to change. Convoys still move slowly across the water. The stakes remain the same. Supplies must reach Britain. Failure is not an option. But something is different now. Escort ships no longer operate in uncertainty. Radar scans sweep the horizon, detecting surface submarines long before they can strike. Aircraft equipped with improved detection systems patrol overhead, extending the reach of protection far beyond the convoy itself. And beneath the surface, sonar pulses cut through the darkness, turning silence into information. German U-boats, once the predators, begin to lose their advantage. In May 1943, losses reach a critical point. Dozens of submarines are destroyed within weeks. The numbers are not just significant, they're unsustainable. This moment becomes known as the turning point in the Battle of the Atlantic. But there is no single battle to mark it. No decisive clash of fleets. Instead, it is the result of accumulation. Radar forcing submarines to submerge earlier. Sonar tracking them once submerged. Long-range aircraft closing the gaps where convoys were once exposed. Each technology alone is not decisive. Together, they become overwhelming. U-boat commanders begin to report an environment where survival is no longer assured. Attacks become riskier. Opportunities diminish. The ocean, once their ally, now works against them. And with each convoy that passes safely, the strategic balance shifts. Supplies flow into Britain more reliably. Troops and equipment build up for future operations. Momentum begins to change. At the same time, far above Europe, another transformation is taking place. The air war intensifies. American bombers push deeper into German territory, targeting industrial centers, rail networks, and production facilities. Missions that once depended on clear skies now proceed through cloud cover, guided by electronic navigation systems. Accuracy improves. Not perfect, but sufficient to disrupt critical infrastructure. And then there is defense. German anti-aircraft forces respond with everything they have. The skies fill with flak, explosions timed to destroy incoming aircraft. But something has changed here as well. With the introduction of proximity fuses, anti-aircraft fire becomes far more effective. Shells no longer rely solely on precise timing. They detonate automatically when near a target, increasing the likelihood of damage. For German aircraft, the effect is immediate. Maneuvering becomes more dangerous. Close formations become riskier. Survival becomes less certain. The airspace itself grows more lethal. Meanwhile, in hidden locations far from the front lines, another decisive element continues its work. Intercepted communications, decoded messages, analyzed patterns. Though rarely acknowledged at the time, code-breaking efforts, such as those conducted at Bletchley Park, provide critical insights into enemy movements and intentions. Convoys are rerouted away from danger. Operations are planned with greater awareness. Surprises become less frequent. Once again, there is no visible moment of triumph, only a steady reduction in uncertainty. Across these different theaters, sea, air, and intelligence, the same pattern emerges. Technology does not deliver a single dramatic victory. It creates conditions where victory becomes increasingly likely. German forces, once able to act with speed and unpredictability, now encounter resistance shaped by information and precision. Their advantages erode, not through one decisive blow, but through constant pressure. And as 1943 progresses, a realization begins to take hold. The war is no longer balanced, not because one side has more soldiers, but because one side now understands more, detects faster, and responds with greater accuracy. It is a shift that cannot be easily reversed, and it sets the stage for even larger operations, where these technologies will not just influence outcomes, but enable them. June 1944. Before dawn, the English Channel is filled with movement. Thousands of ships, hundreds of aircraft, an operation so vast that its success depends not just on force, but on coordination at a level never before attempted. This is D-Day. From the outside, it appears as a massive amphibious assault. Soldiers storming beaches, naval guns firing from offshore, aircraft roaring overhead. But beneath this visible spectacle lies a network of technologies quietly guiding every phase of the operation. Navigation systems direct fleets across open water and darkness, ensuring they arrive at precise locations along the coast of Normandy. Radar monitors airspace, detecting potential threats before they can disrupt the landings. Communication systems maintain coordination between ships, aircraft, and ground forces. Even deception becomes technological. False radio transmissions and carefully controlled signals convince German forces that the invasion will occur elsewhere. Entire divisions are held in reserve, waiting for an attack that never comes. The result is not perfection. Far from it. Landing craft drift off course. Units become scattered. Resistance is fierce, especially on beaches like Omaha. But despite the chaos, the operation holds together. Because beneath the uncertainty of battle, there is structure. Signals continue to flow. Positions are tracked. Commands are relayed. And, slowly, the foothold is secured. At the same time, in the Pacific, a different kind of campaign unfolds. Vast distances define this theater. Islands separated by hundreds, sometimes thousands of miles. Navigation, detection, and coordination are not advantages here. They are necessities. American forces adopt a strategy of selective advance, bypassing heavily fortified positions and targeting key locations instead. This approach, often referred to as island hopping, relies heavily on accurate intelligence and precise execution. Radar-equipped ships detect incoming aircraft earlier, allowing defenses to respond in time. Carrier-based aircraft, guided by improved navigation systems, strike targets with increasing consistency. And as the war progresses, the integration of these technologies becomes seamless. Naval fleets operate with a level of awareness that would have been impossible just a few years earlier. Enemy movements are tracked. Air threats are anticipated. Engagements unfold with calculated intent rather than reactive urgency. For Japanese forces, the effect is increasingly difficult to counter. Attacks that once achieved surprise now face prepared defenses. Movements are detected earlier. Opportunities narrow. The battlefield shrinks, not in size, but in uncertainty. By late 1944 and in 1945, the cumulative impact of these developments becomes undeniable. On the Western Front, Allied forces push deeper into Europe. Supply lines remain stable, protected by the now secured Atlantic routes. Air superiority grows, supported by detection and targeting systems that ensure consistent pressure on German infrastructure. In the Pacific, American advances continue, each operation building upon the last. Coordination improves. Losses, while still significant, become more manageable compared to earlier phases of the war. But perhaps the most important shift is not in territory. It is in control. Control of information. Control of timing. Control of engagement. The Axis powers, once defined by initiative and speed, now find themselves reacting more often than acting. Their decisions are constrained by incomplete information. Their operations disrupted by forces they cannot fully perceive. And in this imbalance, the outcome of the war becomes increasingly certain. Not because a single battle decides it, but because the conditions for defeat have been steadily, quietly established. These technologies, radar, sonar, code-breaking, navigation systems, precision fusing, do not appear in headlines. They are not celebrated in victory parades, but they are present in every successful operation, every avoided ambush, every mission completed with precision. They form an invisible framework supporting the visible war. And by the time the final campaigns unfold, their influence is so deeply embedded that it is almost impossible to separate from the outcomes themselves. Victory at this stage is no longer just being fought for. It is being engineered, an outcome shaped not only by courage and sacrifice, but by the quiet mastery of science, industry, and innovation. A mastery that will leave its mark not just on the end of the war, but on everything that follows. May 1945. The guns fall silent across Europe. Cities smolder, roads are scarred, and millions of lives bear the weight of years of conflict. Germany longer fear annihilation. Merchant shipping, which had been the lifeline of Britain, continues to impress. Communications intercepted and deciphered by efforts coordinated with the Bletchley Park and American cryptography teams have ensured that strategic decisions are informed by accurate insight. Entire enemy movements were anticipated and countered before they could materialize. For soldiers on the front lines, the enemy's intentions often seemed obvious, but this clarity was the result of technology working behind the scenes. Meanwhile, across the Pacific, American advances continue with precision. Island hopping campaigns, supported by radar, advanced navigation, and improved naval coordination, culminate in victories such as the capture of Iwo Jima and Okinawa. Every operation, every landing, every strike reflects lessons learned from technological superiority and industrial integration. The strategic balance of the war has shifted not through dramatic confrontations alone, but through cumulative, largely invisible advantages. For the Axis powers, defeat comes not only from the strength of Allied troops, but also from an inability to respond effectively to forces they could neither fully see nor comprehend. Numbers underline the scale of impact. By some accounts, thousands of ships were saved in the Atlantic alone, countless aircraft losses were prevented, and millions of tons of supplies reached Allied forces precisely because of these technological systems. Casualty reductions, while hard to quantify completely, were significant when compared to what might have occurred without these innovations. These advancements also enabled faster preparation for large-scale operations, such as D-Day, demonstrating the cumulative power of invisible warfighting tools. Yet, for the public and even many military personnel, recognition is limited. Newspapers celebrate heroic soldiers and spectacular battles. Parades honor troops and generals. But the scientists, engineers, and technicians whose innovations quietly ensured operational success remain largely unknown. Their victories are hidden in efficiency, accuracy, and survival, elements that rarely make headlines but fundamentally determine outcomes. In the broader context, the war has exposed a new reality. Modern conflict is not only about manpower or firepower. It is about knowledge, coordination, and technological advantage. The quiet systems operating behind the scenes have proven as essential to victory as courage and strategy. And as Europe begins to rebuild, the lessons of these hidden technologies begin to resonate. Industrial capacity, technological foresight, and intelligence capabilities are recognized as critical instruments of national power, not just tools of war, but safeguards of survival. This realization forms the bridge to the next chapter. The enduring consequences of these innovations, how they shape post-war military doctrine, influence global power, and redefine the very nature of warfare itself. August 1945. The war in the Pacific ends with Japan's surrender, following the unprecedented use of atomic weapons on Hiroshima and Nagasaki. Cities are flattened, millions of lives are lost, and the global balance of power shifts irrevocably. But alongside these visible and catastrophic events, another, quieter transformation has already occurred, one that will influence warfare for decades to come. American wartime technologies, once classified and unseen, now stand as a foundation for future strategy. Radar networks, perfected during the Battle of the Atlantic and European air campaigns, transition into civilian air traffic control and early warning defense systems. Proximity fuses, code-breaking methods, and advanced navigation systems do not vanish with the war. They form the core of Cold War military planning. Industrial innovations also leave an enduring legacy. Assembly line production techniques, standardization of components, and mass manufacturing strategies developed for wartime urgency now inform peacetime industry and global logistics. Factories that once built tanks, planes, and radar equipment pivot to consumer products, yet retain lessons in efficiency, scale, and precision. Moreover, intelligence and information management emerge as central pillars of military power. The success of code breaking, signal interception, and early warning systems demonstrates that the ability to see before being seen is as decisive as numerical superiority. Future conflicts, from Korea to Vietnam to modern cyber warfare, will rely heavily on systems conceived quietly during World War II. Yet there is also a psychological aftermath. Allied commanders recognize that wars are no longer fought solely on courage and numbers. The invisible dimension, technology, coordination, and intelligence, has redefined victory. Soldiers, while heroic, are only as effective as the system supporting them. Victory is engineered, not just earned. The Axis powers, meanwhile, grapple with the consequences of underestimating technological integration. Germany's U-boat fleet, once the terror of the Atlantic, is decimated. Japan's early successes in the Pacific are reversed by electronic detection, advanced navigation, and industrial capacity the nation cannot match. Even tactical genius cannot overcome the systemic advantages the United States has built. By the end of 1945, the war's lessons are clear. Modern conflicts demand innovation as much as manpower, planning as much as bravery, and foresight as much as reaction. Technology, once a supporting player, has proven decisive. As historians later note, the quiet American inventions, the radar arrays, proximity fuses, code-breaking machines, and navigational tools, may not dominate the narrative of heroism, but they dominate the outcomes. They have reshaped strategy, protected lives, and ensured that battles, convoys, and campaigns succeed far more often than chance alone would allow. And from these lessons, a new era emerges, one where warfare, industry, and innovation are inseparable, and where the legacy of the quiet technologies of World War II will ripple into every conflict that follows. War is often remembered through the roar of guns, the flash of explosions, and the faces of those who charge forward under fire. Yet, for every soldier on the front line, there are countless unseen forces shaping the battlefield. Forces that never appear in photographs or headlines. In World War II, these forces were American technologies quietly designed, refined, and deployed to tip the scales of history. Radar arrays scanning stormy seas. Sonar pulses echoing beneath black waters. Proximity fuses detonating above enemy aircraft. Code-breaking machines turning encrypted messages into actionable intelligence. Navigation systems guiding fleets and air squadrons with invisible precision. These were not weapons of spectacle. They were instruments of control, enabling victories that would have been impossible through brute force alone. The individuals behind them, the engineers, scientists, mathematicians, and technicians, worked without glory, yet their contributions were no less heroic. Their victories were measured in lives saved, missions accomplished, and battles subtly altered, often before anyone even realized the danger had existed. They proved that intelligence, innovation, and foresight could match, and even surpass, the impact of sheer courage and manpower. The war they helped win reminds us of a profound truth. History is not only shaped by what we see, but by what we cannot. The quiet mastery of technology redefined warfare, preserved lives, and reshaped global power structures. It set a precedent for future conflicts, where information, detection, and precision would increasingly determine outcomes. In the end, the forgotten American technologies did more than win battles. They transformed the nature of war itself. And though they often remain invisible in the stories we tell, their impact echoes through history, a silent testament to ingenuity, dedication, and the subtle forces that quietly shape our world.